Okay, I'm fine. So this is our 41st lecture. We'll be winding up on excitation systems today, and we'll be seeing SCADA systems in brief. And with this, we'll be ending our syllabus. So I'm happy that we completed our lectures in 41 lectures. So yeah, it's been a very long journey. Okay, let me just go ahead quickly recap the things which we have seen in the previous class. We talked about economic allocation of generator, where we use participation factor concept, which we have already seen before. I just gave you a brief introduction about implementation of AGC, and then we started discussing about the reactive power and voltage control. Here we saw about what all devices are there which actually impact in increasing or reducing the voltage across the network. And we saw some of those devices, their advantages, their disadvantages, where they are used, and if they are used in a transmission system or if they are used in distribution system, how they behave in both the systems. And we also saw about static power compensators. Briefly, we discussed about one of these static power compensator, where you can use inductor and capacitor in parallel to ensure and to maintain the voltage within a particular limit. So you saw how we can change the voltage vertically. Here you saw how we can move the voltage vertically up and down, and how we can rotate the slopes by changing which parameter we have to change. So here XTH has to change, so that means basically the network values we have to change. So network values are basically shunt capacitors, series capacitors, transformer taps, and phase shifting transformers, SVCs, all those things we can change eventually, which will lead to change in XTH. And we saw this composite SVS diagram, where if what happens if particular voltage load change happens, how the voltage will behave, and how if SVS is there, then how the voltage is behaving. So this we already saw that some cases we have shown. And finally, how to implement it. So basically we implement, we get the set points of initial set points of all the SVCs, shunt capacitor. If let's say it's a switched shunt capacitor, or if it is a switched series capacitor, where we have to keep that setting, or what will be the setting of that capacitor, that will be decided by the OPF. And then in the power flow, that setting is fixed, and we can fine tune those settings by using power flow. As I told you before, your reactive power is only considered in ACOPF. It is not considered in DCOPF. So if you are using DCOPF, then you have to adjust using power flows and DCOPF in iteration. So that is a brief introduction what I gave you in the last class. And then we quickly jumped into the excitation systems, which is actually the last part, where we can control the voltage by actually changing the voltage set point of the synchronous generator. So that is anyway they are there in the network, and rest all components are additional. So rest all components are not there naturally, so you have to install those equipment separately. But excitation systems are naturally there in the power system, because obviously synchronous generators are generating the real power, and they can easily support in providing voltages and reactive power. So we saw the basic generator capability, which actually is the limiting factor for excitation systems. So one is rotor insulation failure, which happens because of high voltage, high field voltage. Rotor heating can happen when high field current is there. Even core end heating can happen when under excitation operation is taking place. Even if excessive flux is there, then also heating can happen. And heating, why I'm emphasizing on heating, because heating can eventually burn the laminations inside the rotor coils, and eventually which can lead to turn fault. And as soon as turn fault happens, then there is no option. You again have to basically open the rotor, and then again you have to rewind the motor again. So you again need to remove those coils and install new coils on the rotor if lamination is failed. So that's why it's a very costly and expensive affair. It increases your maintenance cost and it reduces your operation time. So operation duration is reduced when you go for maintenance. So those things, and that's why heating is the key here for excitation system. I also told you that how much is the power consumption required for excitation system, and this is not very small. This is actually significant amount for a big power plant. And also I told you that heating you can exploit by some duration, by some time, and you can overheat for small duration, and then again you can bring the elements or the parameters within limit, so that you can do not continuously strain the machine or stress the machine by heating it, and you can save the machine by going out of or any failure can happen. So this is what we saw in the last class. So I just recapped everything. So I hope everything is clear. Any queries from the previous class? Am I audible, right?
Yes, sir.
Okay, good. So let me just tell you today's class. So today's class, I'll be just telling you about these excitation systems a bit in detail, and then we'll see the SCADA system. So those topics we'll be seeing today. So probably 15 minutes is needed for excitation system and 15-20 minutes for SCADA. Okay, let me just go ahead from here. So as I told you before, that excitation systems, this also, this we have not discussed in the last class. So the previous requirements, so the requirements of the generators, basically what are the requirements from the generator side from these excitation systems. So obviously generator wants the excitation system to be in such a way that it should not heat the rotor, it should not give high field voltage, it should not have high armature current. So those things it has to maintain. But what is the expectation from excitation system from the power system point of view? So power system just wants to control the voltage and enhance the system stability. This is the prime requirement by the power system from the excitation system. And this is eventually to satisfy, means basically from the excitation system to satisfy all these requirements, both from the power system point of view or from the generator point of view. It should be basically the response of the excitation system should be within a specified limit. It should have a limiting and protective function to ensure that excitation system do not damage itself, right? And it should provide sufficient operating flexibility to the system. And lastly, it should be reliable and it should be available whenever it is required, especially during the time of fault and the isolation or the islanded situations where systems are disconnected, right? So these are the basic requirements from the excitation system. So let us see some of the elements of the excitation system here. So basically here, two power systems. So basically this is the grid side, right? Here the generator is there, he is generating the power as well as the voltage. Here you are seeing the exciter, and behind that there is a regulator. So let me just quickly tell you all the components here. So basically regulator, or you know that for exciter generators we generally give DC supply in the field side of the generator. So this regulator the role of the regulator is to ensure that it actually amplifies the control of the exciter. So it actually amplifies the control of the exciter. So basically, whatever input signal is coming from the by the sensors on the right hand side or the grid side, it senses those information and it takes the action. Either it has to amplify or it has to reduce the signal size, amplitude, or the frequency. Based on that, the exciter will change the excitation, and it will eventually change the field of the generator. So this regulator takes signal from few of the devices. One is power system stabilizer. This power system stabilizer ensures that the systems, means the change in the voltage should not be such that it should affect the system stability. So that is PSS is there, power system stabilizer. This gives the signal to the regulator. Another is limiters and protective circuits. Limiters and protective circuits, the main role is to ensure that the exciter and generator itself does not damage by, let's say, voltage is reducing in the grid, and let's say generator does not have the capability to supply that voltage, but because there, if there is this protective circuits are not there, then regulators will continue to provide, and eventually it will be very high voltage at the generator terminal, which will eventually lead to the excess of heating and eventually burn the generator or damage the generator. So that should not happen. So therefore there is a limiters and protective circuits are there, which actually ensure that, okay, that is your maximum capability, or regulators should not go beyond a particular value, right? And lastly, there is a terminal voltage transducer and the load compensator. It actually senses the actual role of this terminal voltage transducer and load compensator is to sense the terminal voltage, and based on that it gives the signal to the regulator how much more voltage is required or how much less voltage is required, if you have to increase the field current or if you have to reduce the field current. That is decided by this terminal voltage transducer and load compensator. So these are the broad components. Let us see in the diagram what exactly, how exactly these elements look like. So basically there are three types of excitation system, and we'll be seeing all these elements of excitation system in these three sections. One is DC excitation system, one is AC excitation system, and another is statics excitation system. So obviously let us see them one by one, and you'll be getting the idea of that. So this is the DC side, this is the AC side, and this is the main generator, this is the DC generator, because the recording is lost, so just wanted to recap. So here this voltage regulator sends the voltage from the CT and PT, and this voltage regulator gives the signal from the DC side and from the AC side, and it compares the signal and give that signal to a motor, this amplidyne. This amplidyne is nothing but it's a motor, and this motor is actually rotating the DC generator. So this DC exciter is nothing but a DC generator, and this DC generator will be having a prime mover, or a rotor will be there, and that rotor has to be rotated to generate that. And this rotor rotation is connected or the field of that generator and the rotor both is connected through this amplidyne. Amplidyne is a kind of a motor, or is kind of a machine which actually amplifies. So just by the name you can guess, amplidyne is actually amplifying the signal. So basically whatever is the signal which is given by the voltage regulator is doing the comparison of the voltage, and that comparison or that delta change will be given to this amplidyne, and amplidyne will amplify that signal to the DC generator, the field of the DC generator, and eventually DC generator will sense that change and eventually change the DC side current for the main generator. So here the current will change for the DC side, and eventually it will change the voltage at the AC side. So this is what is happening in the DC excitation system, and it can be of both type. It can be of manual signal type. You can also have a reference signal here. If you have a reference signal, that means you can manually control the voltage regulator, that is also there. And you can also work the system in an automated fashion. So there are various other, if you go through the literature, there are various other methods for DC excitation system. This is just one of the type, and I'm explaining this for your basic understanding. Right? Any queries so far? Okay, so let us see now AC excitation system. This is again, I'm telling you, there are various other methods for AC excitation systems or various other designs for that, but I'm just giving you one example. So, as the name suggests, it is AC excitation system. So, the main generator is excited by a AC generator, not by the DC generator. So, that's why it is called a AC excitation system. And obviously, because you need to give DC uh, on the this field of the main generator, so therefore you have to use a diode which will actually convert the AC current which is coming from the AC exciter to the DC current. Right. So the idea here is basically you again have CT and PT on the AC side which sense the voltage, and this voltage sense is given to the AC regulator and DC regulator. There are two type of regulators, and they both actually basically do a comparison here for the DC supply side and the AC supply side, and based on that they actually give there is a controlled rectifier. For this they give a firing angle signal that how it has to allow the system to change. So basically this firing angle change is decided by this DC and AC regulator, and based on that this AC generator reacts to that firing angle, and the field of the AC exciter changes based on this controlled rectifier firing angle. And as soon as that value is changing, then the AC exciter will change the current value, and eventually it will change the current of the or DC current of the main generator. So this is the simple diagram. Again, you can have the manual control of that also, and also you can have a automated control also. Both features are available. Again, this is just one of the diagrams for AC excitation systems. There can be many other design for it if you go and see in the literature. So just wanted to give you some basic understanding here. Now let me just quickly, because the recording is gone. So basically, again, this is DC side, this is the AC side. Again, CTPT gives the signal to the AC regulator and the DC regulator. It compares and gives a firing angle to the rectifier. And here, for instead of the movable part which is there in the DC and AC excitation systems, here you have exciter transformer, which actually is kind of a auto transformer, or you can assume it like there are tap changing transformers, and you can change the tap, and eventually, or you can fix a tap to a particular value, and you can again control it by this controlled rectifier, which will again change this firing angle of this rectifier will be changed by these DC and AC regulator, eventually changing the field of the main generator. Right. So, any query regarding this static excitation system? So, again, this design of AC, DC, and static excitation systems are very old designs. There are new designs, new techniques, new methods are there, new. But this is just for your understanding how does these excitation systems work. Any queries? Okay, if no queries, then let me just quickly tell you this about the control and protective functions. So I was always talking about there are some actions which actually do the controlling of the voltage and controlling of the excitation system to eventually increase or decrease the voltage at the generator terminal. And there are some devices or some equipments which are for the protections of the excitation system as well as the generator. So basically, if you see the diagram here, it is again there is generator, and here we have a grid, right? And I'll just explain all the blocks quickly one by one, not going ahead. Just ignore this field shorting for a while. So generator, grid is there, then generator is there, and then there is an exciter, and this exciter is connected again to the DC and AC regulator. Here, whatever is the, because this is the DC side, this is the AC side. So the DC voltage is sensed and it is given to the DC regulator, and there are few sensing things which is given to the AC regulator, which actually compares and give the signal to the exciter. Right. So let me just first talk about the control functions, and then let us come to the protective functions. So control functions is basically, first is power system stabilizer. This actually ensures that the dynamic performance of the voltage change which is happening on the grid side is actually not going into unstable state. It remains stable. So that is ensured by the power system stabilizer. Then you have this voltage sensing and load compensation. It actually, let's say if exciter system, it also senses the voltage in a simple sense. It also senses the voltage, and obviously it is connected to the AC regulator because it is sensing the AC voltage, and it senses and gives the signal to the AC regulator. It also, here I'm also adding load compensation. One more feature of load compensation is actually, let's say if exciter system is unable to satisfy the voltage, then, or rather you can say, if let's say you have to reduce the voltage, just think in that sense, if you have to reduce the voltage in the generator and you have to operate in the under excited mode, so in that case obviously generator may get damaged because of heating, and also load compensation basically mimics the load, and it actually, there are some resistors and reactors which are connected to the terminal of the generator, which can be switched on to basically absorb the voltage, reactive power, and eventually reduce the voltage. So that is the feature of volt sensing and load compensation. Then you have this exciter system stabilizing circuits, which actually stabilizes the control functions of exciter. So obviously, if let's say, because there is some control system which is actually changing the field circuit, and that control system may need to damp out the fluctuations of the exciter system. So for that, there is a stabilizing circuit for this excitation systems. This also ensures the stability of the exciter system. The power system stabilizer ensures the stability of the power system, not the exciter. So that is what is happening here. Right, so these are the control functions. Now let us talk about the protective functions. So protective functions are basically 4 protective functions are there: over exciter limiter, under exciter limiter, V by Hertz limiter, and field shortening. So let me just go about them one by one. So let us start by over exciter. Over exciter is again same logic. If you over excite the system, over excite means you have a high field voltage or high field current. Eventually it will lead to the heating of the machine, and you have to restrict the exciter to go beyond a particular value. The same is logic is there for the under exciter. Here, if you try to reduce the voltage and absorb more reactive power in that under excitation mode, you might be heating the core of the rotor or core of the stator instead of the heating at the coils. So here in under exciter, the heating happens at the core of the rotor. Another is V by Hertz limiter. V by Hertz limiter is again logic is same. If let's say grid side voltage is very high and frequency is very low, so V by Hertz, V is very high, frequency is very low, so V by Hertz ratio will be very high. Eventually it will generate excessive flux. So V by Hertz, if it is high, so the I don't know if you remember this from your machines course from your bachelor's degree, that when voltage is high and the frequency is low, it generate excessive magnetic flux in the generator, and that excessive magnetic flux will eventually again heat up the coils and the core of the generator, and that will eventually damage the generator. So basically, and that is again limited by V by Hertz limiter. So basically, you need to ensure that exciter do not damage the generator. So this is the thing. Now, lastly, field shorting. Field shorting, the idea here of field shorting is basically this happens when, let's say, a short circuit happens at the generator terminal, and whenever there is a short circuit happening at the generator terminal, then what happens is basically the reverse power flow situation can happen. Basically, the current in the exciter system or the field of the generator might become negative, and as soon as that happens, that could actually damage the exciter systems, and on the DC side, it can damage things. So basic field shorting is actually a device which is basically, there is a resistor is there which is installed, field resistor, which immediately gets switched on to die out these negative current, and it avoids the exciter systems to get damaged. So this is the feature of field shorting. Right, so this is the basic understanding of control and protective functions. Any queries here? So, if no queries, the SCADA systems. So basically, before SCADA, it is we are talking about automation, because obviously power system is growing industry. Still new technologies are coming up. Still renewable are coming up in a big way. Still basically demand management is coming up. Even we as a consumer are also becoming aware of the prices of the electricity. As the prices are growing up, we are also becoming much more aware in the system. So in all those activities, power system is not just to be controlled manually. Now you need some automated processes to control power system, and obviously, as a human intelligence is limited. Human intelligence is limited with this big size of the network and system. You need to have some automated activities where you do not need human intervention, right? So therefore automation was extremely needed in power systems, and once we started focusing on automation, power system is just not limited to the electricity. It also needs knowledge of signal processing. It also needs knowledge of wide area networks, data communication, advanced computer applications. So it has now become an interdisciplinary topic. As you all are aware of, that power system involves lot of as we are talking about smart grids, smart cities, these are all basically focusing on automation and intelligent, adding intelligence to the power system, where power system can take actions, control actions on its own, and where human intervention as is as less as possible, right? So if you just connect from the course what we have seen till now, we have seen about so let's say next year at this time we want to control our power system. So first you will be doing, let's say, long term planning, long range planning, which will be for hydrothermal scheduling, right? Then probably, if let's say time comes close to the one month, then you will go for unit commitment. Then let's say if it is coming one day, then probably you will go for again unit commitment, as well as hydrothermal scheduling, which will be short range hydrothermal scheduling. And then let's say if on that day particularly you might be running OPF or economic dispatch, where you will be basically scheduling the generators based on the commitments. Your unit commitment is giving you a signals for unit commitment. And then at the actual day of operation, you will have this this AGC and primary droop characteristics will be there, which will actually primary and secondary frequency load frequency control will be there. There will be AVR, which will actually control the voltage regulator. In all these process, especially at this side, which is actually happening in the real time, you need lot of sensors, lot of measurement devices, and even lot of actuators. So actuators, I'm sure everybody is aware of. Actuators are basically whatever signal you give back to these measurement devices or switches. There are few switches. These actuators will activate those switches if, let's say, you want to do some action. And all these things are happening at the remote location. Practically nobody is sitting near to these switches. They are all sitting at the control center, and they can control all these switches sitting at the control center. Most of the time these switches are basically located inside a forest or inside a densely populated area. So obviously there sending a person to do that action will take a lot of time, and during that time a lot of mishappening can happen. So basically, if let's say voltage is rising or frequency is increasing, you do not have enough time to send anybody to do a particular action to so that the voltage can come within the limit or frequency can reduce. There is no option of that. So you need a automated process, right? So this automation is basically advancement in this automation happened because we have developed various latest instrumentations in these areas. We have lot of intelligent electronic devices are there. You can also call them PLC, programmable logic controllers or computers. They are even more smart. They can automatically take decisions, and you have obviously we these days we have communication is a very influential in all these, because communication is easily available and it is available at a very less cost. And these days even also people are talking about cyber security. You must have heard this term before about the cyber security. So here people have already focusing on the standardization of communication protocol. So for example, like for this electricity signals are transmitted even today. These signals are transmitted not through our regular mobile communication basis or not through our telephone communication. It has a different protocol, it has different signals, and it is transmitted through that. Even I don't know, probably foreign students might not be aware of. In India, we have railway ticketing system, and even in the railway, if you go to the counter to book the ticket in the railway, they do not use our regular telephone lines or mobile communication. They have their own communication protocol and their own communication channel over which they communicate and book the tickets, so that to avoid any cyber attack and any mishappening. Right, so we have developed these technologies which has actually helped us in making power system automated as a broad. So just quickly, I want to give you a evolution how the automated automation happens in the industry, in power industry. Basically, if you see long back before 18th century, obviously human used to do everything. Even the job of machine was done by humans, but or people, but machines, the development of machines happened during that time, which was the first industrial revolution. During the second industrial revolution, now the process control has taken place. Process control is a part of automation where you can introduce some routine functions which will automatically change the signals for machines and operate. But it was in a very initial phases. But now these days, because power system is huge, you cannot avoid going for automation. And we you know that the in initially control equipments, what was there, they were very large and bulky, and control rooms were huge panels were there, lot of wires are there, so that does not make things very easy to add control in olden days. But these days we have a lot of automation, and we have digital computers these days where we can easily program anything on a machine language, and we can get the job done by with these automated systems. So basically major development happens with the development with the integrated circuits and advancement in the communication systems. So these two were the main developments, with technology developments happened, because of which we were able to do this automation in power system. So the actual term for this automation in power system is actually known as SCADA. Just by the name, I hope everybody is aware of it, is supervisory control and data acquisition. So what does this mean, supervisory control and data acquisition? Just by the name you can suggest that you are collecting the data. Data acquisition means you are collecting the data. So you have a lot of measurement devices, you are collecting the data, and then that data is communicated to a central operator, and that central operator can give some control signal. Supervisory control, that's why I'm calling it as a supervisory control, because there is some person or some intelligent computer or that is taking that decision, and that decision is being again communicated to the actuators or these switch controllers located at the place of switches. There those switches can be switched on or off based on whatever is the process. So this is what is happening in the SCADA systems, right? So let me just define SCADA for you. I'll just take probably 10-15 minutes more, and I'll close everything. And just give me 10. You do you have anyone has class at 3 p.m.?
Yes, sir. We have class.
Okay, so let me just quickly wind up in 5 minutes. Okay, so basically, SCADA is defined as the collection of equipment that will provide an operator at a remote location. So obviously, it is communicated. So operator is not located somewhere near those switches, and sufficient information is communicated. And based on that information, you can process that data and cause some action, and that action will eventually change the equipment process without you or the operator being physically present there. So that is actually the SCADA systems, right? And SCADA is implemented in two processes. I told you, one is data acquisition, one is supervisory control, as the name suggests, and it is all automated process, and you can easily see everything in the control room, and you can immediately take action. So basically, just quickly to tell you, the diagram here is you have a power system, you have a measuring elements. Measuring elements means all the measuring devices. Those measuring devices can have some transducers, some AD interfacing devices or AD converters, and they can basically they can convert the signal whatever they are measuring. Either they are measuring voltage, frequency, real power, reactive power, voltage in phase wise. They can measure current. They can measure a lot of things at wherever you have connected that measuring devices, and they can communicate these information to the master station or the control center, right? And these signals what you have sent to the control system or control room, there they can take a judicious or some supervisory decision what they have to do. So if everything is fine, then you do not take any decision till you get some some change is happening. Then you again see, okay, now I need to act, I need to change some switches, I need to change that switch. So I may need to switch on a generator, switch off a generator, switch on a shunt capacitor, or switch on a transmission line, or switch off a transmission line, or change a transformer tap position, anything, any type of any such type of decision you can take, and then again pass on that decision using a communication signal, and then again you might need to convert that signal, which can be easily read by the controller or the actuator, and that will be signal will be given to the control element or the controllers which are placed at the remote location, and then that operation can be done at on the power system. Right. So this is the way a SCADA system works. So this is the very simple explanation for a SCADA system. I hope you got the idea how exactly SCADA system works. In this, there are basic functions. There are four components of SCADA. Basically, one is master station, where HMI is human machine interface. Basically, all the data is coming in on a computer, and a human is sitting on a computer to see that data. There is a communication channel. There is a RTU or IED. RTU is remote terminal unit, or IED is intelligent electronic devices. You can also call them as PLC, programmable logic controller. And there is a field equipment. So field equipment can be either be measurement devices or controlling devices, right? So they are all communicating between each other to eventually send the signal to the master station and send the signal back. So this role of RTU, IED and PLC, they actually sense the data and gives a alert signal. So let's say if everything is fine, they will be idle. If it's some mischievous activity is observed, they will immediately give an alert signal to the master station, and either master station there can be a computer which can take a decision, or a human can be there which can take a decision. So just quickly, remote terminal unit is actually, or PLC, it's basically eyes, ears and hands of the SCADA system. It always keeps on sensing the data. It transfers the data, and again, it can take a decision on its own. It always keeps on monitoring the surrounding, and it always processes the data. Communication systems, there can be a dedicated communication channel for the electrical systems, or there we also call it as there can be a protocol which can be followed for a particular communication channel. Master station is nothing but a human machine. It's a control room where all the data is coming and the processing is happening on that master station. HMI is nothing but computers, where you see big displays there, where you see all the data which is coming there, and operator can take a decision based on looking at those data. Or a smart intelligent computer can be there which can take the decision on its own. So basically, basic SCADA functions are, just give me a minute, I'll close. So it is basically data acquisition, remote control, human machine interface, historical data analysis, and report writing. So at times SCADA is these days are very smart. They can generate the reports on its own. They can do the historical data analysis. HMI, I have told, remote control and data acquisition, I have already told. So these are the advanced functions for SCADA. So these days, obviously, SCADA, they have a different application. If you are focusing from the generation side, so basically SCADA can be used at AGC, economic dispatch, unit commitment, load forecasting, hydrothermal scheduling. For all these purposes, a generation system can use the SCADA and process these applications. There can be, for the transmission system operator, network configuration. They can switch on and switch off the transmission line. They can do state estimation, contingency analysis, OPF, three-phase unbalanced power flow or balanced power flow in the transmission system. So these are the applications of SCADA systems in transmission system side. And for the distribution system, there are fault identification, network reconfiguration, power factor control, three-phase unbalanced power flow. So you name it, lot of applications. You can think of a lot of applications where SCADA systems can be used in the distribution systems. Yeah, just two slides are remaining. I'll close. So basically, the advantages of SCADA systems are basically they are more reliable, because if you are sending a human or a person there, then obviously there is a time involved, there is a money involved, there is a human error is involved. So a lot of issues are there which is removed if your SCADA system is there. Although error is there in the measuring devices, but that error is very less compared to a human error. So that's why the reliability is improved, operating cost is improved, because you need less people now in the company to ensure the for the SCADA or for any measuring or any measurement or control actions. You can do a faster restoration, faster operation of a power system by, you can just sit at a control center, immediately you can switch on or switch off a line just sitting at your control center. So that becomes a much faster operation. Obviously better management can be done. It reduces the maintenance cost, because obviously you are not making any error, because if you do error, then obviously you are switching off and switching on, and every switch has a as you keep on switching on and off, it has some wear and tear involved to it. If you can optimize that, you can ensure that less and less operation can be done. That will eventually reduce the maintenance cost. Human influence and error can be reduced, this I have already told. Faster decision making can be done when you have a smart so all data are coming in a smart way, and then immediately you can use a computer to do that process. Eventually you can use the optimization to basically get the job done in a best possible manner. So these are the advantages of SCADA system. And with this, let me just quickly tell you the last slide, which is about the hierarchical setup of Indian transmission system. As I told you before, at every substation there are RTU, that is remote terminal unit. They are sensing all the data and sending the data to the load distribution center, which is at the distribution level, or load dispatch centers, not load it is LDCs, dispatch centers. And then all these from the local dispatch centers. So in India there are distribution companies, and then these distribution companies send the signal to the state, that is state load dispatch center, and then SLDCs send the signal to RLDCs, which is regional load dispatch centers. So there are regions in within which in one region there can be 5 or 6 or 7 states can be there within one region, and that RLDC is again processing the data and sending the signal to the national load dispatch center, which is sitting in Delhi in India. And these signals are being transmitted at a time rate of 12 to 15 seconds from the at the lowest level. Then at every 2 to 3 seconds or 2 to 5 seconds, it is being communicated to the next upper level, and that is the way the signal reaches to the national load dispatch center. And then the decisions can be taken at every individual levels. Initially obviously the decision is taken at the lowest level first, that is RTU level, then at LDC, then if that decision is not taken, then SLDC, then RLDC, and then NLDC. And that's where that delay is there. So the delay is there to ensure that the decision has been taken at the lower level, so that the upper level do not worry about that. So if in within 5 seconds the decision is not taken, then the previous or the upper hierarchical person will take that decision. So with this, I'll close the session,